Hello everyone, my name is Abdulkader Al-Gailani from Al-Hubaishi University, together with my colleague Dr. Mohammed Al-Hubaishi and Dr. Mohanad Al-Alayedi. I will present our study on Wi-Fi and Bluetooth indoor localization. Our main idea is to show that we can build an accurate indoor localization system using classical machine learning models, as long as we design strong features. We ask the question, can feature engineering alone deliver high accuracy without deep learning? And in this work, we showed that the answer is yes. Here is the roadmap for the presentation. We start with the introduction and the motivation. Then, the dataset overview. Next, we explain our methodology with a focus on feature engineering, which will be followed by the results and analysis. Finally, our conclusion. Our goal is to demonstrate that smart feature engineering is the most efficient path to high accuracy indoor localization. As we see here, why do GPS fail indoors? Firstly, GPS performs well outdoors, but it fails indoors due to several reasons. Multipath interference, signal reflected by the walls or reduced after passing through obstacles. Next is direct line of sight to satellites. However, many environments such as hospitals, offices, and universities require accurate indoor positioning, especially for emergency responses. Wi-Fi and Bluetooth signals are available everywhere, which makes them attractive for indoor localization. The challenge is that these signals are noisy and unstable, which makes classification difficult. Here, in this research, we used IEEE Dataport Hybrid Wi-Fi Bluetooth Fingerprinting Dataset. It includes over 1,000 samples and it is collected from 15 indoor locations across multiple floor levels using 10 signal sources. The dataset is balanced roughly at 72 samples per location, which makes the evaluation fair. The data is also included with real-life environment noises such as wall interference and people moving around. This makes the localization task much more challenging and realistic. Here we see that raw RSSI values are highly unstable, even if the user stands still. The signal can change significantly because of people walking, doors either opening or closing, interference from other devices, reflection from walls, and the difference between floor level. This instability makes raw RSSI unreliable. So instead of directly using raw values, we transform them into stronger and more meaningful features. We start with 13 raw RSSI signals coming from Bluetooth and Wi-Fi sources. These raw signals are noisy and highly variable. Through systematic processing, we transform them into 47 feature engineering features that summarizes the signals and extracts stable patterns. These features give the model much more information to learn from and hence much better results. Here we have our feature engineering used in our research. We have used 6 here. Firstly, simple statistic. We compute basic statistics such as mean, minimum, maximum, and variance. This makes unstable signals much more stable. Even this step alone improves accuracy significantly. Wi-Fi and Bluetooth features. Wi-Fi and Bluetooth behave differently. Wi-Fi has longer range but is more noisy, while BLE is shorter in range, but much more stable. Next is availability. Sometimes signal appear, sometimes it disappears. By checking how often each signal is detected, we can refer how close we are to the source. Floor feature. Signals from other floors are weaker. We encode this behavior so the model can distinguish floor level. Advanced stats. We add entropy, percentile, and other statistical measure to capture more detailed signal characteristic. Stability feature. We measure how stable each signal is across 10 scans. The more the stability indicates that the receiver is closer to the transmitter. In our research, we used machine learning models, and the amount of machine learning, the number of machine learning models we used were 8. So the evaluated machine learning models were 8, which includes random forest, gradient boosting, SVM, KNN, decision tree, logistic regression, naive Bayes, and small neural network. We used 5-fold cross-validation for reliable evaluation. We monitored accuracy F1 score and checked for overfitting. We also performed an ablation study, removing and adding feature group to measure their contribution. Here, we can see our graph for F1 score, test accuracy, cross-validation accuracy, and performance of each machine learning model with the tests. Our best model was random forest. And here it indicates that we have no overfitting, and the model stability is less than 1%, which is the difference between CV and test. Here is why random forest is the most optimal choice. Because of its higher accuracy on noisy data, provides feature importance, fast training, and interpretable. As for gradient boost, which comes very close with 88.95%, and the remaining other models, which are 85 plus. Cross-validation results match our result test closely, indicating strong stability and no signs of overfitting. Here are some key take findings. Our feature engineering plays the biggest role in improving accuracy. It enables models such as random forest and gradient boosting handle noisy RSS signals very effectively. Deep learning is not necessarily for this dataset size. Classical ML performs just as well with far low complexity. As we see, deep learning needs time to process data, and it needs large dataset to process, whereas machine learning can use less dataset and provide results effective immediately. Feature engineering greatly boosts accuracy. Models are robust against noisy indoor signals, and there is no need for heavy deep learning models. The system is fast, accurate, and interpretable. Here, we have ablation. With only raw RSSI signals, the accuracy is 76%. As we added feature groups one by one, the performance increases. It reaches 89.5% with complete feature set. This confirms that each feature contributes meaningful to the model's performance. And summary for our feature engineering. Feature engineering greatly boosts accuracy. Models are robust against noisy indoor signals. There is no need for heavy deep learning models. The system is fast, accurate, and interpretable. The system can run on laptops, mobile devices, or small IoT hardware. It works with existing Wi-Fi and Bluetooth infrastructure. It does not require GPU or cloud computing, making it suitable for hospitals, emergency system, and smart building. Thus, in conclusion, we demonstrated that carefully feature engineering can produce highly accurate indoor localization. Our system achieved 89.53% accuracy using classical machine learning models. The application is efficient and interpretable and practical for real-life deployment. Thank you.